Here we have today's part. This is going to be rather uninteresting as a part, but I am going to, same as the 2 videos ago where I was cutting some steel and I was pushing the face mill as hard as I could reasonably with the current spindle motor. That's kind of what I'm going to do here today as well. This is an aluminum piece that we're going to try to push the shear hog tool from AB Tools as hard as this mill can reasonably push it right now, and that gives me some good data for after the conversion, seeing how much benefit I got out of the new spindle motor. So thanks for watching, and we're going to dive in today. I'm going to show a little bit of CAD today and a little bit of the rendering of my mill, and that'll help illustrate the point of why I'm making this extension and why I haven't needed it before. And then obviously, as in the last few videos, you're going to get to see some machining here, and then this hopefully will wrap up fairly quickly. So here we have the Precision Matthews mill as it was about, I don't know, 3-4 months ago. So as you can see here on the table, I have a single 5-inch vise from Precision Matthews. There's no fixture plate on here, and this is roughly the design of the old motor. So I'm going to take the enclosure off just so you can see a little bit better. And I do have the joints built in, so this should represent the realistic travels of my machine as it stands right now, and this does represent the approximate opening and closing of my old vise. So I'll show you the problem that I'm going to run into here if I don't make this part today. With the head all the way down, and this is with the vise as open as it can be, you can see here that I have quite a bit of extra room on the rear of the vise here. So the distance between the spindle center line and realistically where I could cut, this distance right here by this box is probably about 5 inches, maybe 4 inches on the old setup. You can see the vise overhangs the table here a little bit, and the jaw, or the distance between the back of the vise itself and where the jaw ends, is fairly large on my old Precision Matthews 5-inch vise. And because of that, it really made me push this vise as far back as I could without smashing into the ways in the machine. So that's why I had to get this little bit of overhang. And conveniently enough, when I did that, you can see the spindle center line almost lined up with the vise at full extension or full opening. This distance here, this old vise could hold about a 5-inch part, and I could machine just about the whole 5 inches of it, and it wasn't that big of a deal. I had all this extra room right here that was basically wasted movement because the vise couldn't hold anything right there, but it really didn't limit me because I couldn't machine anything any further back than here because the vise wouldn't open as far. So that is sort of how the machine used to be set up, and kind of gives you a background of why the machine worked perfectly fine the way it was. And we're going to fast forward to roughly what the machine looks like now. Alright, so this does have the new motor on it with some of the mounting hardware and roughed in a lot of the upgrade parts that I'm making right now. Again, I'll turn the enclosure off so you guys can see a little better. And as you can see here, we have the Saunders Machine Works fixture plate that I got designed by the guys over at Saunders, and the 2 M-lock vices, which have been amazing. And these are actually positioned how they are right now because if you can notice, sorry, I go off on a little bit of a tangent here, the vices are certainly pushed over more to the right here, and there's a lot more room in the fixture plate on the left. And the reason for that is this motor contacts the housing of the enclosure. I'll turn the enclosure back on again. I'm limited in my travels by that motor hitting the side of the enclosure, so I can actually travel further in this direction than I can in this direction on the mill right now, and that requires me to offset the vices a little bit so that they're centered in the X travel. And that's why they're that way. I am actually going to, when I take the enclosure off, I'm going to make a little bit of a bump out so that I can get an extra 4 inches of travel in this direction, and then I'll center everything right in the center of the table once I put it all back together again. Sorry, that was a bit of an aside that has nothing to do with what we're doing today. So if we look here, I'll go back to that similar setup that we had before, and this is how it's set up right now, is about an 8.5 inch opening. I can get 9 inches, a 9 inch part if I open this just a little bit wider, but this represents just about the maximum travel of these vices as a single station. And if I were to get it all the way to the front here, you can see the part we're making today is this 3.1 inch spacer. So this is actually going to move the center line of the spindle here 3.1 inches out further toward the limits of the table. And with the table all the way moved toward the back, so Y positive now, you can see I can reach the entirety of a part that would be sitting in here. There's a little bit of excess that I have to the center line of the spindle would actually get taken up if I moved this these jaws all the way back to fit that 9 inch part. Then I'd just be able to reach over the edge here. This jaw would be just past just shy of being past center line here, so I could reach over center line on this jaw. And when I move the table all the way to this extreme, you can see this is about spindle center line right there, and you can see the center of a tool will just reach over the soft jaws as well. And once I put hard jaws into this mill, which they'll typically, into the vise, which they typically will be, that'll even further extend how much extra I'll have on the Y positive for the spindle. So no longer, sorry, I can clear my throat here. No longer am I going to have all this wasted space where the spindle can't reach all this can reach all this extra area, but when I get on this direction, the spindle would stop shy and all of this would be wasted space. So now, if you line this up with the the Saunders Machine Works fixture plate, you can see I can almost machine right up to the edge of the fixture plate. So if I did take these vices off and machine directly on the table, then I'd be able to machine a part that was just about the size of the fixture plate. So that became a necessity once I had this new work holding, and to be able to maximize the the capability of the machine, I had to move the head out that 3.1 inches. Okay, so here we have the part, and again, this is a pretty non-interesting part in and of itself, and the machining on it's pretty straightforward, but hopefully this will allow me to show off that shear hog tool and push the mill in aluminum, so that when we finish the upgrades I can try this test again and see how much harder I can push that tool and how much more material removal I can get out of a 5 horsepower motor. So this hunk of 6061 started off as a piece of 6-inch by 4-inch by 10.5-inch piece of aluminum, as you can see by the grayish brown part here what the stock was, how much material I actually had to remove. This part was one of the largest parts I've ever machined in, actually it is the largest part I've ever made in the machine. So I'll throw up some pictures right now so you can see what it looks like sitting in those vices from M-LOK, but it's a decent hunk of aluminum for a machine this size. All right, so the order of operations here, so setup number 1 that we have here, I chose to machine this side first. This way the block was square. I actually squared it before I started any of this, but didn't bother filming that. So with the square block, it had a flat face in the bottom here to rest in the machine vise, and then once I finished this side and flipped it over, I wouldn't have this boss protruding on the bottom if I had started from the top and worked down. So that was the reason I chose to machine this side first. First thing we're going to do, and again, this was a flat face to begin with, which is why there's no facing pass on here. That was already done. So the first thing we're going to do is machine this bore right here. This is I have it modeled as 2.3656 inches. I did, and you'll see this in the machining footage, I did machine this out with a boring bar, and I used a transfer measurement. So I got a micrometer and measured the actual boss that's on the machine itself, and made this just a couple thousandths shy of that. So it wasn't a press fit, but it did locate on this feature, and then most of the weight should transfer into this cast iron boss that's in the shuttle for the Z head. So first thing we did with the shear hog, machined out the majority of this pocket came back with 2D contour and just cleaned it up prior to the boring operation. This way I could make sure I had an even surface and that wasn't mostly interrupted cut or anything uneven from that roughing pass. After we were done with that, and I manually aligned this when I was done with the boring head and bored it after the fact, so I don't actually have a boring operation built into this. I did that by hand. From there, I had some terrible success in drilling. This was a 1/2 inch drill, trying to push it about 8 times diameter, so I had to go 4 inches deep into this, or about, I guess, 7 times diameter, because I only went to the bottom here, so just over 3.5 inches. But I had a terrible time with this. The motor on the Precision Matthews, that DC motor, just really has absolutely no torque when you try to slow it down at all. And the surface foot that I wanted to run this drill at just caused this to stall and skip, and I had to push it a lot less hard than I wanted to, so there were bird nests, and it just was a bit of a nightmare. So I kind of cut out some of this frustrating footage that I had of me actually drilling this, but the feeds and speeds I used for this are not something I'm going to publish because they're terrible and really not anything I would recommend. So I drilled these holes, and then I drilled the clearance hole for the center here. I am going to use M12 screws in the footage that you'll see of me talking about taking these measurements on how I got the actual dimensions for this. I'll talk about using 1/2-13 and having to bore out the head and having some issues using 1/2-13. Because of that, I decided to use M12, and that'll make this a little bit easier. So the 1/2 inch holes that I have here are clearance holes for M12 bolts. So with that side complete, I flipped it over, re-indicated it in the vise. For this side, this ended up being a ton of material removal. This actually didn't take all that long. I'll say it didn't take all that long. It was about a 1/2 hour to remove all this material. I guess that is a decent amount of time, but for the amount I had to remove on this and the limitations of the mill, I was really happy with this. Removing about half this much material with an adaptive strategy and just a roughing end mill in the past took me quite a bit longer than this, so I was really happy with it. The feeds and speeds we ended up using were 0.6 inches on optimal load and 0.1 inch depth. So again, almost full slotting at 0.1 inches or 100 thousandths depth. So I almost ran this kind of like a feed mill, and I was pretty happy with that. I tried pushing it deeper, and I really just wasn't happy with the sound and the vibration because it is a single fluted end mill. And so I ended up settling on these feeds and speeds, and I really liked them. If you can see, this toolpath looks a little bit weird and it doesn't come to the edge here. The reason for that is I developed these feeds and speeds basically by just skimming back and forth and doing a bunch of facing passes back and forth here until I got the speeds and feeds that I was happy with. So all this material was removed, and I had a bit of a step here, which is why I didn't bother wasting the time and cutting air in that edge here. So I just made some sketch geometry and constrained this tool path to that geometry so it didn't cut all that unnecessary air. So after this adaptive and finishing roughing it out, I came back and did a facing operation with that shear hog as well, and that actually left a pretty great floor finish. But I got less tool deflection by not taking as deep of a cut and not trying to remove as much material all at once, so I wasn't getting any scalloping from tool deflection or anything like that. So I used that tool as a fairly small face mill and just came and cleaned up the face of that. From there, same as before, came in with a 3/8 inch end mill and cleaned up the bore. And you'll see this is actually, it's kind of hard to, you can't see the tool path, but I came below this surface right here. So I didn't want to have, if there was any radius at all right here that prevented the spacer from fully seating, so I made sure that I went below the surface here and then it wouldn't interfere. So that was contour pass, and then I walked that in to be the diameter I was looking for. From there, a quick chamfer. I have not yet actually put this spacer on. The M12 bolts that need to go through here are fairly, I'll say, specialty, so I need T-headed bolts to fit in the rotating slot for the shuttle. and nobody makes an M12 T-headed bolt that's just shy of 6 inches long that I've been able to find. So I got some flange bolts in M12 that are the right length, and I'm just going to cut the flanges and give them some flats and make my own T-bolts. But I'm waiting for those to come in, so I actually haven't test fitted this yet. So we'll see how good I did with measuring these features. So speaking of that, let's jump in and I'll show you how we got the head off and how I came up with this bolt hole pattern. This wasn't something I could find on Precision Matthew's website, so I'll show you how you can measure a feature like this. Thanks for watching. That'll probably be the end of it, and I'll sign off at the end after I show you how to measure this, and I'll see you guys next time. Right now I'm going through and taking some dimensions of the back of the head so that I can reproduce this and try to get in the shot there and try to get as good of a fit as I can for the spacer block. So what I have here is a set of gauge pins. This is a 442. You're not going to be able to see these, so you'll take my word for it. This is a 442 gauge pin. We have a 443 and a 444. I didn't choose those, actually. I got kind of lucky. I didn't choose them because I didn't have 3 of a 443 or something like that. I actually found out that these bores are all different diameters, and if I try to swap the 443 with the 444, if I can stay out of the way, hand out of the way here, that actually won't fit, and that's the same thing for the bore below that. These are actually all about 1/1000th different, which is super convenient because that means that I can get a decent fit with the gauge pins that I have. So with the gauge pins in there, now I just need to come back and measure across all of the high points. So I'll take a caliper. I'm not going to do this super precise on video. I can I'll throw the dimensions up on screen right now as I show you what I'm doing. But you're going to measure across the highest point, so kind of rock it back and forth until the caliper gets to the highest, and then record that measurement. And then from there, you're going to go and you can do it, by hand, and you can math it, but I'm just going to throw it into CAD. Taking into account the diameter of each of the pins, you can get a bolt hole circle, so the circle that goes through the center, as well as the actual positions of each of these pins, assuming that this one is at bottom dead center, which it appears to be close enough for what I'm doing. As long as in relation to each other, they're the right distance apart, then it really doesn't matter. If this was all the way over here, it would just mean that the spacer block would be crooked. But this is close enough to the bottom that I don't think I have to worry of the spacer being too uneven on each side. So once I have those measured, I'm going to take those diameters down and reproduce that in CAD like I said. I took a rough measurement of the bore here, and what my plan was going to be is I set up this bore gauge, and I was going to come in here, actually I already have, come in here and get this dialed in so that I could make this as precise as possible, only just to realize that my boring head actually won't bore out to this diameter. So I'm going to have to do this, and when I say do this, kind of show you what I mean here. Move some crap out of the way. So I'm going to be making the spacer, and on one side there's going to be a bore, and on the other there's going to be a boss to... Sorry for moving so fast. So I will reproduce these features on one side of it, with these being through holes, so that'll be on both sides, and then recreating the boss here, which I measured the length of it as well as the diameter with a micrometer, so I got that as accurate as I could. Something that I found out while I was doing this that's actually pretty exciting. There is a through hole. You can see it better on this side. There's a through hole cast into the center of this bore here, and if you come over here, you can actually see that that boss is tapped. So I checked that I had at least a bolt on hand that was the right thread pitch, so I can go ahead and pick up a new one of those, and that's long enough to go through the spacer, and instead of being limited to the 3 bolts that go through there for holding this head on, I'll actually have 4 bolts that'll go through. So one will come from the back to the front and tighten through here, and then the other ones will be studs coming through the back, and then there'll be nuts on the end of this. Now, as you can see, based on the numbers I've told you, you're not going to be able to fit a half 13 bolt, which is what I plan on using through these holes. So I am going to have to come through once this is all taken apart, and I'll just with a drill widen these holes out to be just over a ½ inch, so there's clearance fit for that. I'm also going to grind down this little lip. It's always annoyed me that I can't get a washer to sit flat on there because the casting line makes it an uneven surface, so I'll fix that. And then the last problem I encountered was, if I look at this half 13 bolt that I plan on using, it will not pass through here, which it obviously has to. I did take a dimension there. I forget it off the top of my head. I'll pop it up on the screen, but I'm going to have to fix that in some way or another. The ideal way to do that would be unmount this, come through and just do a cleanup pass to clean up a little bit of material on both sides of that, and that would allow me to pass this through. Obviously, once I take the machine down to do that, I won't have a milling machine to cut the head with or cut that shuttle with, so that kind of leaves me at a loss. I'll rack my brain. That's a future problem. I can definitely come up with a solution. I could always go different bolts, which I didn't really want to turn down the major diameter of these so they'll fit through, which will give me some flats on these instead of coming to a 60-degree point, which probably would work, and I may end up doing. Or I can try to do some hand work to widen that out, which obviously would be less than ideal because I won't get a great finish. So all things that I'm trying to figure out here, but just for now I wanted to show you how I went about getting all the dimensions I needed for this so I can recreate the spacer.